start off, you can kind of see visually how today's a little bit different. You see variables in your radicand. That's what we're going to learn to simplify today. We really use and abuse one property out of the three we talked about yesterday to make this lesson successful. The property we're going to use the most today is that product property. Namely, because I see three factors underneath that radicand. So I can break that radical apart into three separate radicals around the product. So here's what I mean by that. We can say that 36x squared y to the fourth is indeed 36 times x squared times y to the fourth. And those are products, so we can use the product property to break the radical apart. So to simplify that radical, I'm actually going to simplify three smaller radicals. I'm going to simplify the square root of 36. I'm going to simplify the square root of x squared. And I'm going to simplify the square root of y to the fourth. Square root of 36. You're all smart people. You know this fact. It is 6. I should point out, for the sake of today's lesson, you are just going to assume all the variables are positive. So we can make that assumption. Square root of x squared. Do you know what that is? I think we do. What, Alec, what is it? X. Okay, the question I have is why? Oh, do you know, Kevin? No. That's not my question. My question is, why is the square root of x squared? I see where you're going, but hold that thought, Kevin. He's like one step ahead of me today. The question was, why is the square root of x squared x? X to the first. Why? Do you know? Okay, so x times x is x squared. I think what I hear you saying is that x squared is a perfect square, right? It is the perfect square factor that I need to be able to simplify that radical. Very good. I'll take that. So let's see if we can translate that into taking the square root of y to the fourth. Kevin knows what it is. He just told me a couple minutes ago. Does anybody else? Square root of y to the fourth. Keep in mind you're going to probably have to respond y at the end of all this. Oh, Kevin really wants to. Go ahead. It is yours. It is y squared. Okay, why? It is tough, isn't it? A little something to it. You could give me 2 reasons I could think of. Ooh, he said dividing. I'm wondering if that's where I should take this, because I've taught this in 2 different ways over my career. Gio, what do you have to say? Oh, okay, you don't take the square root of the exponent. That's coincidence that happened. It would be nice if it worked out that way, but indeed it does not. That is not a property we have. We ultimately simplify radicals by finding the perfect square of the radicand. It's coincidence in this case that that's square root of 4 is also 2. What Kevin was saying, he was saying that 2 divides evenly into 4. It goes in twice. And so that's how he got his answer. You could look at it that way, as a division problem. That's true. Why can we look at it as division? Well, if you think back to what we learned about properties of exponents not too long ago, just going to move this a little closer to his friends here. Give me some room to work. All right, this guy here is actually y squared times y squared. So when I break this thing down into its perfect square factors, well, I see that there's 2, you know. So this is indeed like y squared squared. Well, when you go to take the square root of that, it goes away. It's y squared. So that's another reason. You could probably justify your response there. 2 plus 2 is 4. So the square root of y to the fourth is y squared. Okay. So first problem, done. But perhaps you might notice that they're not all, like, nice. Like in part B. So you go along, you're like, oh, look, that's the product property. So I'm going to simplify the square root of 18. the square root of x to the third, and the square root of y to the 7th. Square root of 18. It does break down into 9 times 2. Those are the perfect square factors. You're right about that. And then you square root each piece, so that is 3 root 2. So perfect square factors of x to the third. How do I break that radical down? Anthony? Yeah. And we square root each piece. X squared, the square root of x we just established. That is x. Square roots of x. If there was ever a lesson where it's super important to understand what you're writing, it's probably this one. So if you're like, wait, why did he get x squared times x to be x to the third? Or if you don't understand where the 9 came from, that's the kind of stuff you need to ask. So as you're writing, make sure you understand each and every stroke your pencil takes, okay? Super important for today. Yes, Danielle? So that goes back to our warm-up question for today. How do we know we're done? There's no more perfect nth roots as factors in the radicand. You can't leave it as the square root of x to the third because x to the third has a perfect square factor. X to the third has x squared as one of its factors. So you have to simplify the radical. Does that make sense? Okay. All right. Square root of y to the 7th. What's the perfect square factor? Megan? You could break it down that way for sure, because 4 plus 3 is 7. I'm just going to roll with that. You can do it that way. It's not the way I would do it, but you could do it that way. So y to the 4th times y to the 3rd is y to the 7th. And then you would square root each piece, right? Y to the 4th we've already established when you take the square root of it is going to be y squared. But the square root of y to the 3rd, that can break apart again because as we saw in the previous chunk of the problem up here in the middle, you see that the square root of x to the 3rd simplified. So we're not done yet. So now what would you do, Megan? Yeah, so you would break this radical down again. Square root each piece. So you get y times the square root of y. And then don't forget about your y squared out in front. So you'd have to simplify that a little bit, Megan. So the square root of y to the 7th actually simplifies to be y to the 3rd times the square root of y. There's a little bit of a quicker way to do that. Yeah? What do you think, Kristen? Yeah, that is correct. That's correct, and that's what I would do too. I would have picked something a little bit bigger. She picked y to the 6th times y to the 1st, because y to the 6th, if you just take the square root of that, that's your y cubed. So it eliminates that one step. So what we're starting to establish is this idea that if you want to identify the perfect square factor for a variable raised to a power, well, it's going to be the even number that's less than that power. So if we're taking the square root of y to the 7th, the perfect square factor is y to the 6th. If you're taking the square root of y to the 9th, the perfect square factor is y to the 8th. There's yet another way that you could look at this. I don't know if anybody noticed a pattern so far. Well, this problem isn't quite done yet. So let's see if I can keep going with this method, and let's see if you get a shortcut out of this. That's what I'm hoping, because that's a lot. That's a lot to look at. So there's a little bit of a faster way to do these problems. I want you to kind of look for the pattern with what's outside our radicand, what's radical, what's inside the radicand, and then the index. Lastly, we have to kind of pretty this answer up a little bit. We can't leave this on a test and hope that I'll be able to decipher your work necessarily into a correct final answer. What we're going to do is take everything that's outside the radical and leave it outside the radical. And everything that acts as a radicand is going to stay under the radical. I always think it's like this the Vegas commercial. What happens under the radical stays under the radical type thing. So we got 3x y times the square root of 2xy. Oop, yep, thank you, sorry. I dropped my cube there. Forgot to highlight it. Thank you. Right there, yeah. So, this is your answer. Right there. Maybe you'll get the shortcut after I do one that's a cube root problem. You okay, Emily? Okay. All right, so now we have cube root. 27x to the 5th, y to the 3rd. So we're going to use our product property to break it down into smaller pieces. Cube root of 27. Hopefully you know that one. That's just 3. Hey, you might even know already the cube root of y to the 3rd. Cube root of y to the 3rd? Y to the 3rd is a perfect cube. Yeah, so that's just y. Okay, now we have to ask ourselves, what's the perfect cube factor of x to the 5th? Kristen. Yeah, x cubed. X to the 5th breaks down into x cubed times x squared. And then you can cube root each piece, right? So what we get out of this is x times the cube root of x squared. I'll bring down my 3 and my y. The last step in doing this problem is to kind of, I always say pretty it up a little bit. You take everything that's outside the radical and put it outside. Everything that's underneath stays underneath. So this is going to be 3x y times the cube root of x squared. Now, does anybody see a quicker pattern? A little quicker way to do it? Yeah. What do you think, Alec? Uh-huh. Yeah, so what is that pattern between those numbers that you're saying right now? What operation are we actually doing? Close. Aw, when I say it, you're going to be like, oh. So I don't want to rob you. Ailey, it's division, yeah. So here's what Haley's talking about. You ready? You don't have to write this down purely for your visual entertainment. What you're going to go ahead and do is think about it this way. You have, let's say we did the cube root of x to the 3rd. You could ask yourself, how many times does 3 go into 3? 1 time. So x was our answer. The other thing you could think about, well, let's say it's not so pretty. Let's say we have the cube root, like we just did, of x to the 5th. You ask yourself, how many times does 3 go into 5? 1 time. How many are left over? 2. Whoa. Mind blown. Okay, let's make up a weird one. Somebody give me a weird index. 10. That's pretty weird. 10th root. Somebody give me a weird exponent. Take it easy on me. It's 9th period. 23. I heard that. I like the prime one. So we'll do C for Claire because she's like chiming in up here. So you ask yourself, how many times does 10 go into 23? 2. How many would be left over? 3. So there's your shortcut. If you were like, how do I find the perfect cube factor? What are you talking about? It's division in disguise. So that could bring you a little bit of comfort. It's crazy. Go ahead, make it weird, Luke. Get it. So, like, give me something. 12. See? Like that? Okay, so that's when you'd use your product property. You do the square root of 12, square root of c to the 23rd. Like that? Oh, a number in front. You still have to simplify that the way we did yesterday. Okay, I lied. If it's a number like cube root of 8, you know 8 is like 2 to the 3rd. So 3 goes into 3 one time, you get 2. It's not shorter though. That's the thing. So yes, you could do it that way. It's not shorter. What's your homework tonight, my people? Yes, independent practice 2. It does say there's a worksheet on there, but because of the 2-hour delay day, I wanted to give you time to do independent practice 2 in class and then give you the worksheet. So you get a little bit less practice, but we'll see how it goes. Oh, the fraction quotient property. We'll talk about it as a warm-up tomorrow. Give me 1 second.